Let x1 through x10 be a random sample of size 10 from a normal distribution. So it's still normal. With mean 0 and variance sigma squared. This text uses a lowercase n for normal. We've always used a uppercase. Find a best critical region of size alpha equals 0.05, meaning probability of a type 1 error is 0.05, for testing the null hypothesis that the population variance is 1 against the alternative hypothesis that it's 2. Okay. We are testing a variance here, not a mean. So that's your first hint that perhaps we're going to get something different than we did for the mean. This is, before we do this, realize this is not like comparing two variances that we did learn a little bit about in problem stats, where we use the F statistic. We looked at ratios of S1 squared divided by S2 squared, the ratio of the two sample variances. It's not the quite same thing here. We only have one population, not two. We're testing the value of one variance. Okay, so let's work this out here. X1 through X10, they picked a particular value of n. Could have maybe done this. Maybe I will go ahead and calculate the likelihood ratio, leaving n unspecified, though in the end we'll plug in n equals 10 to help us actually finish the problem. These are all normal. I'll use a capital N. Mean of 0, variance unspecified, sigma squared, because we are testing the variance. We're testing the null hypothesis that the variance is 1 versus the alternative hypothesis that the variance is 2. And again, when I compute the likelihood ratio, for the sake of generality, I'll call this thing sigma sub 0 squared, and I'll call this thing sigma sub 1 squared. But then we'll ultimately plug those numbers in, 1 and 2. Again, we're going to take alpha to be 0.05. The question says, find a best critical region of size alpha. Find a best critical region or rejection region. Both terms are used. Of size alpha. By size alpha, it's just a shorthand way of saying probability of a type 1 error is alpha. It's not that some literal physical size of the region is alpha. Okay, it's not that the length of the area is alpha. I mean, alpha could perhaps be thought of as an area under a curve, but don't take the word size too literally. It's just shorthand. So by the name in Pearson lemma, what we need to look at is the likelihood ratio, which means we should first figure out the general likelihood function. Well, I guess I could just go ahead and start computing the ratio right away. So again, here's the likelihood ratio. In the general case, it was theta 0 divided by L of theta 1. The theta here is sigma squared, so I could write sigma sub 0 squared divided by L of sigma 1 squared. We need the PDF for a normal. We used that in last Thursday's example. 1 over square root of 2 pi times the standard deviation, right? Not the variance down here. Standard deviation, sigma sub 0, times e to the negative x minus mu squared over 2 sigma squared, right? But mu here is 0. keep things a little simpler looking. Oh, and I'm making a mistake already. It's the product of these things. Xi squared over 2 sigma 0 squared. Ignore the smudge. And the bottom, it's something similar, except replace the 0 subscript with a subscript of 1. This quantity being less than or equal to some number k is the form that a best critical region takes. The set of points in 10-dimensional space, x1 through x10, satisfying such an inequality is the way, the form the best critical region takes. What is k? We'd have to figure it out. It depends on what alpha is. K depends on alpha. Yikes, not so simple looking. Certainly the square root of 2 pi's will cancel. I mean, we'll have 1 over square root of 2 pi to the nth power in both the numerator and denominator, so those will cancel. Here we'll have a sigma sub 0 to the nth power in this denominator up here and a sigma sub 1 to the nth power after I do the product down here, and I can flip the bottom one. I could write this ultimately as sigma 1 to the nth power over sigma 0 to the nth power. And then with the e's, you're multiplying a bunch of things here. Let's be careful. You have e's to a bunch of different powers that are all being multiplied. You got to add the exponents. So I can write it without the product symbol anymore. I can just write e to the negative summation. It goes from 1 to n of xi squared over, it's the same denominator up there, 2 sigma 0 squared divided by e to the something very similar, except it'll be a sigma sub 1 squared. And then both the numerator and denominator have e's. I could write it as e to a single power. Effectively, take the top exponent and subtract the bottom one. Maybe I'll write this sigma 1 over to the nth over sigma 0 to the nth as sigma 1 over sigma 0 to the nth power, quantity to the nth. And then I'll just have a single e. The power of the, I could bring, let's see. Oops, I made a mistake. This should be squared right there. I forgot my square there. E to the, I could factor out this summation sign when I do the subtraction. Well, maybe, okay, let's be slower. Let's just continue taking it step by step. Try not to make a mistake. Subtract the bottom, it's going to be plus because I'm subtracting a negative. Forgot a square again there. Got to change that to a square. It's so easy to make a mistake. Looks like we're there. This being less than or equal to some k, again, is the form of the critical region. All the points, the xi's where that's true, where sigma 0 is fixed and sigma 1 is fixed. Sigma 0 is 1, sigma 1, I guess, is square root of 2. But if we're going to have a chance of finishing the problem, where we find the best critical region when alpha is 0.05, a specific alpha, not a general alpha. You gotta simplify this somehow. And the typical thing to do is take logs of both sides now, right? With maximum likelihood estimators, we take logs of the likelihood function right away and differentiate. Here, we get to this inequality before we take logs. It's not that you always necessarily have to take logs, but it's often useful. We'd like to kind of isolate the summations, perhaps. Yeah, take the log of both sides of the inequality. The logarithm is an increasing function, so the inequality stays the same direction. ln of a product is the sum of the ln's. So we'd have the ln of this thing plus the ln of this thing. ln of this thing by property of logs. I could write it like that. I could also write natural log of sigma 1 minus natural log of sigma 0. I think I probably won't bother. And then the log of this e to this power just becomes the power. Trying my very best not to make any more mistakes here. It's looking better. There's no more e's, and the summations, in a sense, you could start to imagine you can isolate them here. For one thing, you could subtract this from both sides, and for another thing, out of these two terms, you could factor out the summation. Would it be good to add these fractions first to get a common denominator? Maybe. I think I'll just factor it out first. So we got the summation. I goes from 1 to n, xi squared. I factored it out. What's left over is -1 over 2 sigma 0 squared plus 1 over 2 sigma 1 squared. And I brought the other thing to the other side. Like that. I need to divide both sides by this now. It probably would be best to simplify it. For one thing, it's not clear whether it's a positive or negative quantity. So I think if we get a common denominator and simplify it, that'll be a bit more clear. Common denominator would be 2 sigma 0 squared times sigma 1 squared. So let's see, this would become, with that common denominator, negative sigma 1 squared plus sigma 0 squared over 2 sigma 0 squared sigma 1 squared. Certainly the bottom is positive. What about the top? Okay, now here we need to go back and look at our actual form of our hypotheses here. Sigma 1 squared is bigger than sigma 0 squared for this example, certainly. And at this point, even in the general case, let's assume sigma 1 squared is bigger than sigma 0 squared. In other words, we're doing a right-tailed test effectively, in a sense, that we're not using an inequality for the alternative hypothesis. So that means negative sigma 1 squared plus sigma 0 squared is actually negative. That's good to know. So that changes the direction of the inequality when I multiply both sides by the reciprocal of this fraction. Summation I goes from 1 to n of xi squared must be greater than or equal to, not less than or equal to. It's a right-tailed test. Summations being greater than or equal to. The reciprocal of this times that. 2 sigma 0 squared sigma 1 squared over negative sigma 1 squared plus sigma 0 squared, which of course I could have written as sigma 0 squared minus sigma 1 squared, times natural log of k minus n natural log of sigma 1 sigma 0. This, in effect, is just another k. Call it capital K. Have I finished the problem? No, I haven't finished the problem yet. I haven't yet found the best critical region. I'm getting there. I've got now a simpler looking expression, statistic, and a simple inequality involving that statistic. It's got to be bigger than or equal to something. Hope that makes some sense. It's a sum of squares. They're not the sum of the xi's themselves. The xi squared, that's, I guess, intuitively related to a variance, and it is, effectively like a right-tailed test. The alternative hypothesis value is bigger than the null hypothesis value. This should be somewhat intuitive, but not obvious. Should I divide both sides by n? I guess I could. If I do divide both sides by n, the result is not x bar on the left. If I had to call it something, I'd call it M2, right? Our old friend M2. I'm not going to do that. But if I did divide both sides by n, I'd call it M2 because it would be a natural estimator for the second moment of the random variable, e of x squared. Think about the method of moments. You tracking with me here? You feeling awake? Got to pay attention. Any questions? Please stop me if you got a question. I mean, it's just algebra in a sense, but it's very tricky algebra. How do I finish the problem? Well, one thing that would be good to do is plug in the numbers. Sigma 0 squared is 1, sigma 1 squared is 2. Sigma 1 itself would be square root of 2. Not sure if I did that when I was working through it yesterday. N is 10. Plug those numbers in. We could actually figure out what capital K is, in terms of little k at least. Sigma 0 squared is 1, sigma 1 squared is 2, sigma 1 itself is square root of 2, n is 10. Plug all those numbers in here, and this becomes 2 times 1 times 2 over negative 2 plus 1. We don't know little k, leave it as a little k. Natural log of little k minus 10 natural log of, I guess it'll be square root of 2. Actually, what we're doing right now is not absolutely necessary, but I want to do it anyway. What's really more necessary is just to figure out the capital K. But I, just for the purposes of completeness, would like to figure out what little k is anyway. Kind of like what I had you do for your extra problem. Maybe this will be an extra problem if I modify it a little bit for the next assignment. I really don't have to plug the numbers in there. I do need to know their values, I think, but I don't know that I need to plug them in there. As far as this textbook's problem, based on what I remember the answer in the back of the book was for this one, I just figure out capital K. But how do you figure out capital K? We want alpha, the probability of a type 1 error, to be 0.05. What would I need? I need to figure out the probability of the summation being bigger than or equal to 0.05 if the null's true. Why? Why am I saying that? I need to figure out capital K so that the probability of the summation being greater than or equal to capital K is 0.05 if the null is true. Why am I saying that? Because it's the critical region. Yeah. But I want alpha 0.05 to be the probability of a type 1 error. When this is bigger than K, that means you're going to reject the null. If the null is true, you want the chance of that happening to be 0.05. So I got to figure out the distribution of these things here. We're not done in the complication level of this problem yet. It's not super simple still. What I meant to say, it's not super simple after this point. We got to figure out the distributions of the squares of these random variables. Now, I haven't looked to double check, but I think maybe in this textbook, it was just a theorem what the squares of those random variables would be, their distribution. I don't know where it is, if it is in the text. We're gonna have to figure it out. We've done something very similar to this before, though. If X is normal 0 sigma squared, what is, I'll call it Y equals X squared. In other words, what's its distribution? We've done this before in the case when sigma squared is 1. We've squared standard normal random variables before, Z squared. I think we did it even a couple different class periods and said that to figure out the distribution, we found that it was chi squared with 1 degree of freedom. Well, it's a little harder now. Sigma squared is not necessarily 1, although it would be if the null is true. Could we still figure out the distribution even if we don't specify what sigma squared is? Yep, and we can even use the same method. Your old friend, CDF technique. CDF method. What's the CDF of capital Y? As always, it's this probability. But Y is X squared. X can take on positive or negative values. This is really equivalent to the probability that the absolute value of X is less than or equal to the square root of Y. Which by symmetry, I mean, that's the same as the probability that X is between negative square root of Y and positive square root of Y. By symmetry, that's the same as 2 times the probability that X is between 0 and the square root of Y. That's symmetry, right? It's a normal distribution centered at 0. And that would be a difference in values of the CDF of X. That's symmetry. This is also symmetry equal to 0.5, right? We are talking a normal distribution here, centered at 0. Not the standard normal distribution. You know, back a month and a half ago when we did this kind of problem before, sigma squared was 1, I called this capital phi. Why did I call it capital phi? Just because it's a standard thing to do. Nothing special, it's just what people do. But sigma squared is not necessarily 1 here, so I don't want to call it capital phi. But this is 0.5. It's a normal distribution centered at 0, mean of 0. Distribute the 2 back through. 2 times 0.5 is 1. There's the CDF of Y in terms of the CDF of X. So the PDF of Y is the derivative of its CDF, which will be 2 times the derivative of the CDF of X evaluated at square root of Y. Then by the chain rule times the derivative of square root of Y will be 1/2 Y to the negative 1/2. So it simplifies to the PDF of X, evaluated at square root of Y. The twos cancel, you end up dividing by square root of Y. So now we do our lookup in the table. Well, maybe I should just do it from memory here. 1 over square root of Y, we already wrote down the normal distribution PDF before today. 1 over square root of 2 pi times the standard deviation, which is unspecified, sigma, times e to the negative, replace x with square root of y. Square root of y squared over 2 sigma squared. So this simplifies a little bit to say 1 over square root of 2 pi sigma y to the negative 1/2 e to the negative y over 2 sigma squared. If sigma is 1, that's the PDF of a chi-squared with 1 degree of freedom. But I'm not saying sigma is 1. I wonder if we're only going to have time for this one example. I was hoping for a second example. I think we'll have time to start a second example at least. And maybe the homework will be to finish the second example. If I can't quite finish it, we'll see. What's this the PDF of? Not normal, because the y to the negative 1/2. Looks like the best possibility is either a gamma or a chi-squared. In either case, we're using a y here instead of x. The power of the y was negative 1/2. So if it's a gamma, alpha is positive 1/2. So that alpha minus 1 is negative 1/2. And if it's chi-squared, the gamma over 2 would have to be 1/2. So gamma would have to be 1 degree of freedom. It must not be matching this though. It can't work. I mean, for one thing, you've got to, it can't be chi-squared because you've got the sigma squareds there and a sigma there. No sigmas in there, no other parameters in that exponent of the e, for example. But there is an extra parameter up there in the exponent of the e, beta. If it's going to match the gamma, beta would have to be 2 sigma squared. Because that's what I'm dividing by there. And alpha would have to be, to make this exponent negative 1/2, alpha would have to be 1/2. So it possibly looks like it could be a gamma with alpha equal to 1/2 and beta equal to 2 sigma squared. Does it work? We'd have to check that the bottom of the fraction there. Hopefully I've not made a mistake. The bottom of the fraction there is the gamma function. If alpha is 1/2, it'll be evaluated at 1/2, which I believe, if memory serves me right, I think this does equal square root of pi. Beta to the alpha, beta would have to be 2 sigma squared. That's getting raised to the 1/2. This is supposed to be gamma of alpha times beta to the alpha. If it's going to work, this is what it would have to be. I should have this memorized. Is capital gamma of 1/2 equal to square root of pi? Memory serves me right. It is gamma of 1/2 is square root of pi. Yes, okay. This is square root of pi, 2 to the 1/2, sigma squared to the 1/2 is just sigma. I'm happy. Matches. Looks like y, which is the square of x, is gamma 1/2 comma 2 sigma squared. That's the alpha. That whole thing is the beta. Still not out of the woods though. The woods of difficulty. The valley of the shadow of death. Good, because we had to sum those things. Oh, no, you're serious? Sum independent random variables. Do we have to do a convolution? No, let's just use moment generating functions. That's right. That's the easier way to go. Convolution might be necessary when you don't know the moment generating functions, but we do. That alpha is 1/2, beta is 2 sigma squared. If we're adding n independent random variables that are of this form, we multiply their n moment generating functions, which all have the same form. And what's going to happen if you do that? You're just going to keep adding the exponents that involve negative alpha. You'll get a negative 1/2, minus 1/2, minus 1/2, minus 1/2, minus 1/2. How many times? N is 10. 10 times. 10 times negative 1/2, negative 5. The exponent would become negative 5 when we add 10 such random variables. N is 10. In other words, the sum is going to be gamma as well, with alpha equal to negative 5. And beta is still equal to 2 sigma squared. Moment generating functions and the fingerprint theorem ultimately imply that this statistic, I goes from 1 to 10, xi squared, I'm making it a capital X now, is gamma 10 times 1/2 is 5, and the beta stays the same, 2 sigma squared. So now I can finish the problem because I can use technology, Mathematica, for example, to figure out what the probability of such a statistic being greater than or equal to something is, set it equal to 0.05 if I assume the null is true, and solve for the k. If I divided this by 10, it would be an estimator for e of x squared, the second moment of the random variable. I don't have to do that here. I don't have to bother with that here. I know the distribution of this, so I can just use that. Technology or a table of some sort is necessary, but let's see. And I'm assuming the null is true when I do this. So I'm assuming sigma squared is 1. So that this becomes 2. This is gamma 5 comma 2 if the null is true, which you want to assume if you're going to calculate alpha. So I really should do the CDF of a gamma distribution. Alpha is 5, beta is 2, of x. What is that formula? It doesn't involve elementary functions, gamma regularized. So there's nothing I can do really by hand, so to speak. I've got to use technology. I'm doing is I'm setting 0.05 equal to alpha to be the probability of a type 1 error, to be the probability of being in the rejection region of this summation being greater than or equal to something unknown. That's what I got to solve for, the capital K. Assuming the null is true, meaning assuming sigma squared is 1. Because the greater than or equal to there, that's really 1 minus the CDF. Complement of the CDF. Will solve work? I'm not so sure. If I set the complement of the CDF equal to 0.05, can I solve for x? Okay, evidently it did work. I mean, we could check it by plugging it back in. I wasn't expecting to solve to necessarily work. I was expecting maybe having to use find root. Seems to have worked. In general, see, solves things algebraically speaking. In general, if solve doesn't work, or if n solve doesn't work, you have to use find root. And find root is more of a numerical process here, so it's not trying to solve things symbolically. Give it a guess, like, oh, okay, how about 18? Yeah, it gives the same answer. So 18.307, that is the capital K. So capital K is 18.307, i.e., the critical region or rejection region is when this summation is greater than or equal to 18.307. Is that the right answer? I think so. If I recall correctly. That's right. Look in the back of the book. What problem number was this? 7.10. An even problem, the answer is there. Yep, there it is. What's the rejection region in terms of the likelihood ratio? Okay, a little exercise for you to do. Set capital K equal to 18.307 and solve for little k. What kind of value should you expect for little k? Well, in the homework problem you have for today, I think it was what, when I fixed the mistakes, was it like 0.3 something? Not positive, but I'm expecting just generally speaking, a relatively small value for little k. Intuitively, why? The likelihood ratio being small intuitively should be evidence against the null. Why? Because intuitively you're saying when it's small, the numerator is smaller than the denominator to make the fraction small. At least for a discrete random variable, that would mean the probability of sigma squared equaling sigma 0 squared is a lot smaller than the probability of sigma squared equaling sigma 1 squared. If we were talking about discrete random variable, which we're not, though, right? Discrete random variable PMFs, probability mass functions give actual probabilities. With continuous random variables, these likelihood functions are not actual probabilities. They are joint densities, but to find actual probabilities, you have to integrate them. But it's still intuitive that, you know, if this likelihood is small compared to that, you're saying the likelihood that sigma squared is sigma 0 squared is smaller than the likelihood that sigma squared equals sigma 1 squared. So it's sort of like strong evidence that we should reject the null in favor of the alternative is what I'm trying to say. So there's some intuition to this. Neyman-Pearson lemma wasn't just thrown out, pulled out of thin air. They had some intuition that this kind of thing would work, and they were able to prove it. But this is a little bit of a surprising result. Unexpected. You wouldn't imagine your test statistic involving necessarily your variable squared. Could I add more to this problem? Could we figure out the power of the test? Sure. The power would be the probability of being in the critical region when the alternative is true. The power would be 1 minus beta, and it would be the probability of being in the rejection region when the alternative is true, assuming sigma squared is 2. And you could use technology for that as well, except you'd have to plug in sigma squared as 2 and use a gamma 5, 4 distribution instead of a gamma 5, 2 distribution. Maybe I will have you do that as a homework problem, okay? Maybe no homework problems from the book this time. Maybe it's all extra problems that I just write. I think I will do that. I'll have you figure out that power. Use Mathematica. Sigma squared root 2, you'd be using a gamma 5, 4 distribution. I didn't have to. I was just trying to write something that had to equal 0.05. If I just use the CDF, I set it equal to 0.95. It's because this inequality is a greater than or equal to instead of a less than or equal to.